Thanks. So I will be talking about some nonlinearities, looking at that non-local diffusion model, and in particular, I'll be looking at like a nonlinear diffusion model. So applications of that, sort of trying to model something like image processing, some collective behavior, maybe some sort of groundwater infiltration, heat radiation, and plasmas. All of these are sort of diffusion type effects, but the system is actually a little bit nonlinear, so we sort of have to take that into account. But what we want to do is take this nonlinear diffusion, something we see a lot in some classical PDEs models or classical differential equation models, and expand them into the non-local framework. So the reason we want to do that, right, is that it gives us some benefits in terms of giving some physical interpretations to things that maybe don't have very much differentiability, like that dynamic fracturing, the image processing, that kind of thing. You can also capture things like non-Fichtean diffusion, and it allows for a lot of sort of playing around with an adjustments in terms of being able to tune your model into exactly the physical situation that you're looking at. And we'll see that in terms of what we're going to call the kernel function, which we'll introduce when we define these functions. But sort of looking at a couple of pretty strong examples of how we would use non-local operators. One is on that left there. Imagine sort of you have a balloon that you're popping and the structure itself is fracturing, right? So maybe your domain is fracturing, it's not smooth. Non-local operators are great for that kind of thing. Or on the right-hand side, sort of imagine you've mixed up maybe some water and oil, two things that don't actually mix. And we want to be able to sort of have this discontinuity in the function itself or the state of the system in what would actually be a smooth domain. Both of those types of sort of bad things in your models that would be difficult with some classical PDEs, we can capture really easily with those non-local operators. And then of course, when you get something good, you usually also have to deal with some drawbacks there. So even though we do have what we want, sort of this ability to really fine tune our models, it can be difficult to calibrate the model just because there is so much adjustment that you're allowed to make. We're also going to see this concept of an interaction horizon for a non-local model. And that interaction horizon doesn't always have a clear physical choice. So it's sort of similar in terms of something that is hard to calibrate for your model. And then lastly, for that physical interpretation, we're going to actually see in these non-local models that I can't just deal with boundary data, right? So for instance, if we were maybe dealing with a heat type problem, I would take the temperature on the outside of a volume. For non-local problems, we need to have an entire volume worth of data for the boundary data, and it's actually going to be in the same dimension as our domain. And so that can be difficult to get all that information. And sort of mathematically, right, we also want to think about, is the math going to be a little easier for us here? And the answer is yes, of course it is. That's why we're, bothering to do that. So non-local operators can act on functions which are just integrable. They don't have to be continuous or differentiable, right? Which allows us to look at those sort of messier physical situations. As a consequence, that makes the possible solutions for our models quite a bit larger, right? A larger set of possible solutions. And we've also seen that these non-local operators have proven useful in some specific situations, such as problems involving Sobolev spaces and those Navier-Stokes equations. And again, benefits to drawbacks, right? So these non-local operators, even though they can act on functions which are not as nice, right? We also sort of get some not as nice framework as well along with that. So for instance, the non-local Laplace operator lacks some compactness, which we would have expected from that classical model. And then also things like the non-local Poincare inequality doesn't give us a higher degree of integrability, and also, it's still just being developed. So there are some things where maybe it's not that we don't have something, like the way the Laplacian lacks compactness, but we just don't know if we have something. So for some cases of non-local models, we don't necessarily get that fundamental theorem of calculus. And since Helmholtz-Hodge decomposition was just recently formulated, so some things are a little bit in flux, which can make it a little difficult to really fully use these models. So jumping into actually some of these models, some of these definitions that we're going to use. So here we're going to use this one-point non-local divergence operator, which is going to be that integral operator. Here you will see, so when I was talking about sort of calibrating that kernel operator, that's going to be our function alpha here. That will be referred to as our kernel. Then we'll also look at the non-local gradient operator, which is just the adjoint of the divergence operator that we would expect in that classical framework. You'll notice it's not actually an integral operator, but it does play in nicely with that divergence the way I'm expecting it to. We're going to use a handful of assumptions on that kernel. And it seems like there's a lot, but it's just essentially a nice function that says when the points are close together, I'm going to give it a lot of weight because nearby points kind of mean more in non-local operators, right? Something right next to you or a heat value that's right next to the value you're at is going to be much more important than maybe a value that's quite a bit farther away. We also want it to be non-negative, rotationally symmetric, and we're actually going to bound the behavior specifically between these two exponentials, right? Or something that sort of lies in between these two lines. Right? I want it quite large when the distance between my 2 points is small, quite small going out farther. And then I also want to give myself this sense of a interaction horizon that is truncated at a specific point. So that alpha function, right, we're going to let it sort of go out to some standard delta for its default. And then what we're going to look at in this presentation is what happens when I allow that delta to get smaller and smaller, or do what we call localizing the operator, right? Instead of looking at the non-local sort of type of the operator, looking at points around the point of interest, I'm going to sort of shrink in until I'm really just looking at that point that I care about. A couple of other things we're going to use with these operators are what we call the domain and the caller, which I mentioned briefly in that motivation at the beginning. So you'll have sort of a standard domain the way you're expecting, something nice and smooth. And then we have to introduce this caller because you'll notice from my operators, right, this alpha operator is going to be non-zero for every point delta away from everything in my domain, which means that for every point in my domain, I need to be able to get at least delta away for what I consider the boundary. So our caller is sort of that non-local analog to a boundary, but it's in the same dimension as my domain. Right, so you can do sort of what you would expect to do with these non-local operators. You can take the divergence of the gradient to get a Laplace operator. And then this is sort of the first case we're going to see of what happens when we localize, what happens when we sort of crunch down that domain that we're looking at for each specific point. If we get that delta down to 0, just really focusing in on that single point. So what's going to happen is if I allow delta to shrink down to 0, and I introduce a little bit of a scaling here that is in terms of delta. And as delta shrinks down, the non-local Laplace operator converges to the standard or classical Laplace operator at a rate of delta squared. So this is a pretty standard proof in the non-local theory. You can see it in quite a few different places. In this book chapter in particular, they have sort of some proofs that can be adjusted depending on the regularity of your system U. So that's a nice result to see. And we're going to kind of be pushing this type of result into that nonlinear diffusion framework. So just to give us like a sanity check, do we care about these convergence results? Yeah, they're kind of a big part of this non-local framework, is saying if I make a operator that looks like a different classical operator that I want to look at, right, will it localize to what I'm expecting? So for instance, the biharmonic operator, we can get convergence there, and we'll also look at not just convergence of the actions of the operators, but convergence of solutions to systems that deal with those operators as well. So for instance, here we have a result sort of twofold. The first is that the non-local biharmonic converges to the classical biharmonic, and also solutions for analogous systems dealing with that biharmonic are going to converge to each other as well. So mostly a lot of results sort of in these linear systems. We also have some results for Poisson equation. And there are a few results kind of cropping up for nonlinear solutions. But we really do want to flesh that out and get larger and larger classes of nonlinear systems. So for instance, here we have this result for a non-local P Laplacian. And we get that classical solutions to the classical system are converged to by the non-local system with that P Laplacian. So sort of introducing some kind of nonlinearity is what we're looking at, getting that convergence still. So there were sort of a few classes of operators that I wanted to focus on in terms of getting convergence of the non-local nonlinear into the classical. In particular, here we're going to focus on this divergence of f of u, the gradient of u. The f of u, the Laplacian of u is a fun exercise. It's definitely a straightforward one. And then this P Laplacian is one that we're still working towards. So kind of this focus here is that divergence of f of u, the gradient of u. Again, that's our non-linear diffusion in the non-local framework. So first thing to look at, do the operators converge to one another? So when I localize down, when I make that delta as small as possible, I'm going to localize to what I expect with the classical operators. So I'm going to need some pretty hefty regularity in terms of my functions u and f. But if I do give myself some fairly good regularity there, I will get convergence at a rate of delta. for those two operators. So let's sort of look at a little bit of what that proof does. So just starting straight out with this definition of the divergence of f of u, the gradient of u, we'll add and subtract, we'll add 0 and sort of break into two separate terms. And I want one of them to converge to the divergence of f of u times the divergence of u squared, the other to go to f of u, the Laplacian of u, right? Because then I can combine those together, get back to what I'm looking for, the divergence of f of u, the gradient of u in the classical setting. So the second one is the more straightforward one, a little bit easier. We can sort of pull everything we don't want out of that integral, and we actually end up being left with the non-local Laplace operator, which we have seen a few slides ago. That converges at a rate of delta squared to what we're expecting, that f of u times the Laplacian of u. The other one is sort of the one that doesn't play as nicely, that didn't give us the results as nicely as we wanted them to be able to. So in this next one, right, we end up doing some Taylor expansions with some remainders. We want certain parts to go to 0, certain parts to sort of converge to what we want them to do. And it turns out that if we introduce the same scaling as with the Laplacian, like we want scaling to be the same in both, we will get the convergence we want, but actually at a rate of delta instead of delta squared. So it's really just in getting this very last term here to converge to 0, we get it at a slower rate than we were hoping to. So pretty much in any linear system you come across, you'll get that convergence at a rate of delta squared. I was really hoping I'd be able to get that convergence rate of delta squared here, but it turns out that nonlinearity actually introduces this slowing down of the rate of convergence with that delta. You can also leverage this result, this pointwise result that we proved to get L2 convergence of the operators. We don't actually have a rate for that one, but they do converge as well in L2. And after looking at those operators, we do want to look at the solutions to analogous systems using these operators. So system 1 here has those non-local operators. System 2 has the analogous classical operators. And we want to see, do these solutions here, do these u deltas converge to these u's? Do they converge to those classical counterpoints as delta gets small? So first we need to make sure that we have solutions to that non-local system, right? So we're going to leverage a paper by Foss-Radu and Wright, which does actually give us existence of some solutions to that non-local system. Now that we know that the solutions exist, now we can sort of show that they converge the way we want. And it turns out we need some very interesting regularity conditions here. So we need everything we needed for that pointwise convergence, right? That sort of pretty high regularity on U and on F. And we're also going to need some lower bounds for the infimum of that function f. So some lower bounds, and actually ones that do not look particularly friendly. But if we introduce both of those, then there is a convergence at a rate of delta, right, at the same rate of the operators even, convergence at the rate of delta of those two solutions. And the proof here, so the proof for this one actually relies really heavily on the non-local Poincare inequality, which was introduced by Foss. I am fairly confident that there's at least part of this that I can get rid of sort of more easily than some of the other conditions. I think that there's a result that I can use to get rid of at least this nasty bit of this lower bound for the infimum of f of u using some gamma convergence results. And so that would at least get us to a place where all of our bounds on m, don't depend on themselves, at least on both sides. They give us sort of a more straightforward bound on those. Okay, so you'll notice, right, and I've mentioned it a few times, these conditions are not friendly to work with. And we want to make sure that there's even some non-trivial solutions to these, some non-trivial cases. And so you can kind of construct them. We do construct them starting with U and F and sort of constructing H from there instead of starting with H and figuring out what the solutions are. But there are definitely quite a few non-trivial systems that we can have satisfy these restrictive assumptions and therefore get that convergence of the solutions. So for instance, U being something like an exponential bump function, something with compact support that is sort of a very nice differentiable function, and F of U being bounded, and I can shift it up to be as high as I need it to meet these sort of minimum requirements here. And then H just being, what you would expect, the divergence of F of U, the gradient of U. So moving forward from all of this, right, so we really just have shown convergence of operators and solutions for one specific class of that nonlinear diffusion operator. So working still with that specific class, We want to work on relaxing and removing some of those restrictive conditions, right? It's not going to be possible to remove all of them. There are going to be some cases where F is too rough or U is too rough so that we cannot get that convergence, but we want to definitely see something a little easier than sort of those C4 conditions and those really intense conditions on the infimum for that F function. We also want to provide some numerics to verify those convergence rates, right? So we saw in the proof that we only get that delta convergence. We want to verify that that is actually as fast as we can get. I'm fairly certain that it's as fast as we can get, but I do want to make sure that it's as fast as we can get, not that we actually are getting that delta squared and we're just not seeing that in the proof. Also like to explore some diffusivity in a non-symmetric type setting, right? So instead of just having the f of u of x, maybe having in something a little bit non-symmetric in terms of the x and y terms to see if we can still get that convergence. Looking at different boundary conditions, right? We so far have just been analyzing systems with Dirichlet boundary conditions, so making sure that using some Neumann or mixed boundary conditions, we could get those same results. Consider some nonlinear higher order problems. And then also consider some regularity in terms of solutions. Some of the linear cases have been analyzed, but we want to explore that regularity in these nonlinear cases as well. Thank you very much for your time.